In video 61 of our series on tensor calculus, we're going to derive the basic metric objects for each of our sample surfaces. We'll look first at the cylindrical surface. There we said that our surface coordinates are going to be just theta and z. Theta is the angle that our little door makes with the x-axis, and z is just the vertical distance here. Okay, and of course our ambient coordinates are just our Cartesian coordinates, x, y, and z. And then we said that our parameter equations are going to look like this. X, y, and z are functions of theta and z, just like this. Okay, so from here what we want to do is to derive, first of all, the shift tensor. And this is our formula for the shift tensor. The elements of the shift tensor are just the partial derivatives of each of our ambient coordinates with respect to our surface coordinates. So let's run through them. The partial of z1 is going to be the partial of x with respect to theta. So x taken with respect to theta is just going to be minus a sine theta. And then the partial of y with respect to theta is a cosine theta. And then the partial of z with respect to theta is just 0 because it's not dependent on theta. And then we'll run through each of them again with respect to z. So x with respect to z is just 0. Partial of y with respect to z is 0. And the partial of z with respect to z is just 1. So there's our shift tensor right there. And it looks like this. That is our shift tensor for a cylindrical surface. Okay, from there what we want to do is to derive the surface covariant basis vectors. And we'll use this formula for that. It's just the contraction of our shift tensor with each of the covariant basis vectors in the ambient space. And those, of course, are just x hat, y hat, and z hat. So we're simply multiplying. So, for example, for S1, we're multiplying everything in the first column here, where alpha is equal to 1, by each of the respective basis vectors in our ambient space. And likewise, the S2 is going to be a product of everything in this second column by our covariant basis vector. So it's going to look like this. We're taking each of these guys, multiplying by the respective basis vectors, and we're getting this. So this equals this equals this, and of course there's no term for z. Likewise, we go down this column to get this one, and the only one that's non-zero is the third one, so that's what we get. All right, next thing we want to do is to find the surface covariant metric tensor, and that's this equation. It's simply the combination of all the possible dot products between these two values right here to form a matrix. And of course, that's easy enough. S1 dotted with itself is going to be a squared sine squared plus a squared cosine squared, which resolves to simply a squared. And then S2 dotted with itself is just 1. And S1 dotted with S2 is 0, so that gives us these terms right here. Okay, now remember that the square root of these diagonal elements will give us the magnitudes of each of these vectors, so we can plug those in here. Next thing, let's calculate the, what do we want to do next? I guess the volume element. So the volume element, square root of s, is just the square root of the determinant of this tensor. And that determinant's easy since it's a diagonal matrix. We just multiply the diagonal elements together. So the determinant's a squared, so the square root of s is going to be simply a. So there's our volume element. And then next thing, we want to invert this matrix. You'll remember that the contravariant metric tensor here is defined as being the inverse of our covariant metric tensor. So the product of these two will give us the Kronecker delta or the identity matrix. So we simply need to invert this matrix, and because it's a diagonal matrix, that makes it easy. We simply invert each of the diagonal elements like this, 1 over a squared and 1, and we've got the inverse of our covariant metric tensor, and that gives us the contravariant metric tensor. Okay, and now we can use this in conjunction with our covariant basis vectors to find the contravariant basis vectors. It's simply the contraction of this contravariant metric tensor with these basis vectors. So we're going to multiply each of the diagonal elements here by each of the basis vectors respectively, and we're going to get this. So we have this row right here multiplied by this term to give us this, and then we have this row multiplied by 1 to give us this. And that then is our contravariant basis vectors. And of course the magnitude of those is found the same way as before, so the diagonal elements here, the square root of those elements will give us the magnitudes of each of these contravariant basis vectors. Alright, that's all stuff that we've done before, it's just a review. But now what we want to do is to find the inverse of our shift tensor. And to do that, we're going to need the formula that we derived in the previous video for finding the inverse of the shift tensor. We do that by contracting the shift tensor itself with the covariant metric tensor in the ambient space and the contravariant metric tensor in the surface space. Okay, to help us out here, I'm also going to make a copy of the shift tensor. So this is the tensor that we're going to use here, and then this tensor is this one, and of course we know that this is just a diagonal matrix with ones going down the diagonal. Okay, so let's take an example here. Let's see what Z11 is going to look like with alpha being on top here. Well, that's going to be the expansion of Z11 times S11 times Z11, and then it's going to be, we've got two dummy indexes here, J and beta, so we'll iterate through J to get Z12 times S11 Z21 plus Z13 S11 Z31. But then we've got to do it all over again as we iterate the value of beta. So we'd have Z11 S12 times Z12 plus Z12 S12 Z22 plus Z13 S12 Z32. Okay, so for each value of J that can be 1 to 3, there are two values of beta that can be 1 or 2. However, the only element of Z that's non-zero is Z11, so all of these are knocked out because the first factor is not equal to Z12 and Z13 are equal to 0. Likewise, S12 is equal to 0, so this gets knocked out. And of course, this guy is just a 1. So the point here is that the value of Z11 is just the product of Z11 times S11. So multiplying this item by this will give us this value. Okay, and likewise, if we went through the same analysis, we'd find out that the second element here times this one gives us the second element of the first row of our inverse. In other words, here's the result. You'll find that we take each of the elements in this column, multiply by this element in our contravariant metric tensor, and that'll give us the elements of this row and you can see how that works. This times 1 over a squared, this times 1 over a squared, etc. Likewise, we take all the elements in this column, multiply by this element in our contravariant metric tensor, and we get this row, 0, 0, and 1 times 1. So that's how this works to find the inverted shift tensor. Okay, now I'm sure that you can see it here that the elements of our inverted shift tensor are just the components of this contravariant basis vector. Here, this element and this one are the same as this, and the one here is the same as the element right here. Well, that's not a coincidence because you'll remember that this exists. The contravariant basis vectors here are just the contraction of our inverted shift tensor here times our contravariant basis vectors in the ambient space. So the fact that this and this match up is not a coincidence. It's going to happen every time. And because of that, it's actually easier to take this relationship, once we know these, and just reverse engineer the inverted shift tensor. So we could go through this if we want to, but this is a much easier way to do it. Find the contravariant basis vectors first, and then these components are the elements of our inverted shift tensor across the board. All right, before we move on, I want to do one final thing. You'll remember in the last video that we derived this expression, and we said that it should be equal to the Kronecker delta. If we contract the shift tensor with its inverse, we're supposed to get the Kronecker delta alpha beta. So let's see if that's true. So if we're contracting in that direction, then what that means is we're going to multiply every element in this row times this column to get this element. We multiply every element here plus every element there, we'll get this. The product of every element here with this one will give us this, and the product of every element here with this will give us this one. So let's do it. Negative 1 over a times sine theta times negative a sine theta is just positive sine squared theta. And 1 over a cosine theta times a cosine theta is just cosine squared theta. And 0 times 0, of course, is 0. So sine squared theta plus cosine squared theta is equal to 1. Just what we'd expect. Okay, now this term times 0 is 0. This one times 0 is 0. 0 times 1 is 0. That means that this is a 0. Then we take the elements in the second row times the first column. 0 times this one plus 0 times this plus 1 times 0 is again 0. And finally, the last row times the second column. 0 plus 0 plus 1 gives us a 1 here. So we get the Kronecker delta, or the identity matrix, just as we would expect. Okay, so let's move on now and take a look at the spherical surface. For the spherical surface, our surface coordinates are just theta and phi. Theta, of course, is the angle made from the z-axis in an upward direction all the way around to the z-axis pointing downward. Phi is the angle made by our little door with the x-axis as it swings around in that direction. Okay, then the ambient coordinates, of course, are just our Cartesian coordinates of x, y, and z. And as we derived them before, the parametric relationships look like this. So here we have x, y, and z all as functions of theta and phi. Okay, I'm not going to go through the detail we just went through. I'm going to let you do most of the algebra on your own. I'll just guide you through the process. The first thing we're going to do is to look at the shift tensor. And to do that, we just take the partial derivative, first of all of these elements with respect to theta, and that'll give us this column of results. And then we take the partial of each of these items with respect to phi, and that'll give us this column. And that's our shift tensor. Okay, now given the shift tensor, then we can derive the covariant basis vectors just by using these as the components of the vector here, here, and here. And these items in the second column are the components of our second basis vector. All right, next thing we'll do is to derive the covariant metric tensor, and we do that just by forming the dot products with each other. So S1 dotted with itself, if you dot this with itself and simplify it, you'll get a squared. If you dot this one with itself and simplify, you'll get this. And then you'll find if you take the dot product of S1 with S2, you get the value of 0. And as before, if we look at the square roots of these items, we'll get the magnitude of our basis vectors right here. Okay, next thing we'll do is to find the volume element, and we do that by finding first of all, the determinant of this matrix, and because it's diagonalized, we just multiply the diagonal elements together. So the determinant of this matrix is a to the fourth times sine squared. So our volume element is just the square root of that, giving us this value for our volume element. All right, next we want to invert this covariant metric tensor to get the contravariant metric tensor. And because it's a diagonal matrix, we just have to invert the elements of the diagonal. So that's simple enough. All right, next step will be to combine the covariant basis vectors with the contravariant metric tensor, and we can track those together and we'll get the contravariant basis vectors, and they'll look just like that. Okay, well, as always, the magnitude of those vectors will be the square root of our diagonal elements. So here are the magnitudes of the contravariant basis vectors. And then the inverse shift tensor is trivial. We just take the components of this vector to form row 1, and then we take the components of this vector to form row 2. And that's all there is to it. Okay, well, let's move on then and take a look at the torus. For the torus, our surface coordinates are theta and phi. Theta is the angle as the point moves around the big circle here, and phi is the angle as the point moves around the smaller circle around the tube itself. Okay, and as before, the ambient coordinates are x, y, and z, and our parametric relationships this time look like this, as we have derived them in a previous video. Okay, now again, I'm going to move pretty fast and just outline the solution. You can do the algebra to validate the results. First thing we'll do is to find the shift tensor, and we do that simply by taking, first of all, the partial derivative of these values with respect to theta, and that'll give you this column. And then if we take the partial derivative of these values with respect to phi, we'll get this column, and that's the shift tensor. Okay, next that leads directly to the covariant basis vectors, because these three values in the first column are the components of S1, and these values in the second column are the components of S2. It's that easy. Okay, the next step would be to find the covariant metric tensor, and we do that by finding the various dot products. S1 dotted with itself, if you dot this with itself and simplify it, you'll get this expression. And if you dot S2 with itself, right here, you'll just get b squared. And then you find the dot product of the two, one with the other, is just 0. Okay, and that in turn, of course, if we take the square root of our diagonal elements, we'll get the magnitude of these vectors right here. And what's next? I guess we'll do the um, volume element next, so let's do that. We first of all have to find the determinant of our covariant metric tensor, and that's just the product of these guys right here. So the square root of that product is going to be our volume element. It'll look just like that. Okay, the next step is to invert our covariant metric tensor. And again, because it's a diagonal matrix, we just invert each element on the diagonal. And that gives us this guy right here. And when we contract this with our covariant basis vectors, we're going to get our contravariant basis vectors. And they look like this. Next, if we find the square root of these items, we'll get the magnitude of our contravariant basis vectors. And finally, the inverse of the shift tensor is trivial because all we're doing is taking these components and forming this row. We're taking these components and forming this row. And with that, we're done. We've now seen how all this works for each of our sample surfaces. Now, I can't overemphasize how important it is for you to go through these examples until you can derive all the results on your own. I can explain it to you, but I can't understand it for you. So you're the only one who can know when you really understand it. Okay, in the next video, we're going to take a look at the metric equation and the arc length as they relate to surface geometry.